Hello, my name is Oliver Meis and I head the Research and Development Department here at ECOROLL. Today, I would like to introduce you to the process of machine hammer peening, the MHP process, in more detail and introduce it. First, I would like to classify the process within the mechanical surface treatment processes, such as I have brought you 4 different processes here that you will hear about repeatedly when you deal with mechanical surface treatment. One is roller burnishing and the other is deep rolling. In these 2 processes, we have continuous treatment, meaning my roller body is continuously pressed into the surface with a rolling force, rolls off this surface, and is virtually in continuous contact with the respective surface. This results in a very uniform surface texture. I often achieve textures that really resemble a mirrored surface. I achieve extremely low surface roughness and I have a very continuous and highly uniform load on my surface. The other 2 methods are shot peening and machine hammer peening. These are both processes where we do not have continuous contact of the tools with the surface, such as in the shot peening process, a blasting medium is shot onto the surface, which is accelerated by air pressure or by a centrifugal wheel, and then shot onto the surface, resulting in small, tiny micro impacts. And these micro impacts are distributed stochastically over the entire surface, creating an almost uniform and evenly distributed treatment. But there will always be areas that are more or less processed, so we never have an exactly predictable surface structure in certain scenarios. And although there are many simulation approaches in a certain manner to somewhat predict the surface structure, the exact representation of a surface can never actually be anticipated with shot peening in reality. The MHP process, or machine hammer peening, is a method that, in fact, positions itself somewhat in between. We do not have continuous contact of the tool with the surface, but we have a very controlled process in a very precise manner. That means I have a hammer or a hammerhead that is repeatedly and periodically hammered into the surface and moves in a controlled, precise and deliberate manner across the surface. Predicting the surface structure is already much better here, but it remains a discontinuous process, and thus a cratered landscape is left on the surface. Even if it is very smooth, it remains visible. This improvement is notable, but the process still has gaps, leading to an uneven surface. I will show you what this looks like later. How does the MHP process work now? In machine hammer peening, the hammerhead is periodically struck into the surface at regular intervals and then moves forward in a controlled manner, such as that means we can continuously and efficiently work on the surface. We do have individual and distinct impacts, but when we talk about a surface, we can move in a meandering pattern over it and treat every area of the surface. The essential parameters we have here in the MHP process are the impact energy, which is crucial for the degree of deformation. We have the frequency at which the strike is executed, and then we have the feed motion and the path spacing, which essentially determine how much overlap I have between my individual strikes, both in the feed direction and perpendicular to it, essentially to the next path. I must, of course, always ensure that I have a comprehensive treatment, that I do not leave out any single area of the surface, and that I always have the appropriate overlap between each strike. Other parameters that are often mentioned include various different tilt angles, such as how the tool is inclined to the surface, and also crucially important, the diameter of the hammerhead. So, in a similar manner to rolling, we have a tool size here too. The larger the hammerhead radius, the deeper the penetration depth and the effect of this penetration depth, but also the smaller the deformation. We will see that in a moment. Basically, there are different types of tools for hammering. There are systems that work electromagnetically. For those, I need an electromagnetic generator, which allows me to very precisely control the acceleration of the hammer onto the surface. The whole thing can work pneumatically, the whole thing can work piezoelectrically. This means that I have a piezo actuator that briefly expands and thereby drives this hammerhead onto the surface. Or, as in our specific case, I can have an electro-pneumatic solution that we have. Here, a pneumatic cushion is built up through the careful rotation of a spindle or a wobble plate, and when it eventually discharges, a striker is accelerated and forcefully hits the actual hammerhead, which is then firmly pressed into the surface. And so, In our case, we have a system that operates without an additional external energy source. What surface quality can I achieve with hammering? With hammering, due to this discontinuous and repetitive process, I end up with what I would call a cratered and uneven surface. This cratered surface is naturally leveled, and I can significantly press down the roughness peaks from the previous processes, resulting in a smoothing of the surface quality. But it remains a discontinuous process, which is also still clearly visible and evident. Here you see 4 different examples of surfaces. This component was a 42 CRMO4, which was slightly hardened, so it was approximately at 47 HRC. And if I now process this component using different hammers, you can already see that with the same impact energy, for example, the impact energy is not sufficient to completely push away the roughness peaks from the previous process when using the largest ball radius or hammerhead radius. There is only a slight smoothing. On the other hand, if I use an 8 mm ball insert, the impact energy is completely sufficient. I get an absolutely uniform surface. I have completely and entirely nothing left from the previous treatment. And that is also comparable when I take a softer sample. Naturally, if the sample is softer, I penetrate deeper into the surface, can deform it more easily, and thus obtain a smooth, albeit visible, surface structure. Sometimes, when hammering, you might even intentionally aim to achieve a specific texture. There are various research studies that investigate different ways and whether I can structure this hammerhead. Can I attach any pins to this hammerhead that penetrate deeper into the surface, so that I achieve a basic smoothing, but can also imprint so-called lubrication pockets into the surface? This would also be possible with hammering. The most essential reason for hammering is always hardening. With hammering, I have impact energy, I have significantly greater deformation, I have an impulse effect, and this leads to significantly more compressive residual stress than in other processes. The compressive residual stresses generated during hammering here are similar to those produced during rolling. I have compressive residual stress on the surface, which usually intensifies a bit more and then approaches zero at some point. The difference from deep rolling, however, is that this occurs at significantly greater depths. The most important parameter affecting residual stress during hammering is indeed the so-called impact energy. The more energy I apply to deform the material, the deeper the compressive residual stress will be, meaning I can introduce more compressive residual stress. To highlight the difference between a rolled and a hammered sample, I have brought this diagram here once more again. Here we have 2 different publications that were conducted on the same material, and we looked at the different penetration depths of the compressive residual stress. And you can see here that with machine hammer peening, or the MHP process, we indeed have a very significantly greater penetration depth. And that's despite the fact that I'm at the maximum hammering energy here. The hammering system can't generate any more hammering energy. And I have a comparable processing ball head geometry. So I worked with approximately 8 mm for hammering and about 6 mm for deep rolling. Yes, it is smaller, so the depth effect is also slightly reduced, which is why this diagram needs correction. But the fundamental tendency is that through hammering, I can introduce significantly deeper compressive residual stresses, and I can use that, for example, when I have particularly large components. For large components, I need deep compressive residual stress to significantly extend the lifespan. And for that, I usually need very high rolling forces in deep rolling because I need large rollers, and then I also need large rolling forces, large machines, and everything becomes bigger to introduce these deep compressive residual stresses. With the MAP process, the advantage of doing it impulsively, we have no impact on the spindle, we have a recoil-free system because it is decoupled within itself. You accelerate this hammerhead, which strikes the surface, introducing deep compressive residual stresses. But your machine can theoretically be a simple robot that holds this tool and guides it along a path. But you really don't need a very enormous machine tool that can indeed handle these high forces. I have reached the end of this short video. I thank you for your attention, and if you have any questions about hammering, deep rolling, or other mechanical surface treatment processes, please don't hesitate to contact me or my colleagues at ECOROLL AG.